In this video, we're going to look at a new distribution called the t-distribution. We just finished constructing confidence intervals on hypothesis test for mu if sigma, the population standard deviation, is known. Okay, and that's where we did x bar plus or minus z star times sigma over the square root of n. Okay, that was our confidence interval. And we also found z-scores for test statistics for hypothesis tests. Okay, so that's what we're referring back to if you know what sigma was. Okay, so however, in practice, it is generally unrealistic for us to know the value of sigma. Okay, so in real-world examples, we usually don't know what the population standard deviation is. Okay, so how we're going to handle that is use this new distribution called the t-distribution. So if you have an approximately normal distribution and you do not know sigma, okay, and again, that is the key. If we don't know what sigma is, then we use a new distribution called the t-distribution. The t-distribution will substitute the sample standard deviation s in place of the population standard deviation sigma. Okay, so we're going to use s in place of sigma. The graph of a t-distribution is very similar to the standard normal curve. As n increases, okay, so as your sample size increases, the t-distribution gets closer to the shape of the standard normal z-distribution. Okay, and there are tables in the back of the textbook, okay, that you can find the t-distribution in. Okay, so as the sample size gets larger, the t-distribution gets closer and closer to a normal z-distribution, the standard normal z-distribution. Okay, so t-distributions have more area in the tails than the standard normal distribution. Okay, so I'll explain degrees of freedom in a few minutes. It has to do with the sample size. Okay, n-1 is your degrees of freedom, which we'll get to in a minute. Okay, but the basic idea here is the smaller sample size with these three curves will be the first dashed one right here. Notice how there's going to be more area out here under this dash curve, okay, under this one, than there is under this one, than there is under this one. Okay, so basically what's happening here is the sample size is increasing. Okay, so as the sample size gets larger, the area out here gets smaller and smaller. So as n gets larger, so if you take samples of size, say 4 compared to sample size 10 compared to sample size 30, okay, as that sample size gets larger, the dashed curve will get closer to the standard normal curve, okay, which is the solid one that's graphed here. Okay, notice in the center of the normal curve, the standard normal curve, is higher than the dashed curves with the smaller sample sizes. Okay, so basically, you're losing area with the smaller degrees of freedom or smaller sample size. You're losing area in the center of the t-distribution and adding it to the outer tails. Okay, so the t-distribution is very similar to the normal curve, okay, with its properties. Okay, it's bell-shaped and symmetric around the mean. Okay, so the mean is right in the center. The total area under the curve is 1 or 100%, just like it was for the standard normal curve. The mean, median, mode are all 0, okay, which again is basically saying they're right in the center of the curve. We have this new idea called the degrees of freedom, okay, which is n-1, which is your sample size minus 1. So up here, when it says 2 degrees of freedom, it meant you had a sample size of 3. Okay, so 3 was your sample size. 9 degrees of freedom meant that there were 10 in your samples. Okay, so you took samples of size 10. Okay, so 10 minus 1 is 9. And we use the t-distribution when the population is normal or approximately normal and sigma is unknown. And again, sigma being unknown, that is the key. Okay, so in order to find values for the t-distribution, critical value t star, so instead of z star, we're looking up t stars now. We're going to find the t star value for each confidence level with a given sample size. So if we want to have a 95% confidence level, or we're going to construct a 95% confidence interval, and there's 21 in our sample size, well, we know that the degrees of freedom, I'll just say df, will be 21 minus 1, which is 20. So in our table, Okay, you go to, again, this was table C in the Moore book. The T distribution for critical values. And this is going to read a little bit differently than the Z distribution. Notice the degrees of freedom go down the side and confidence levels across the top. So if we want a 95% confidence level, okay, we find 95%, and we had 20 degrees of freedom, so we find the column for 20. Go across to the 95% confidence level, and that gives us 2.086. So our T star value would be 2.086. In terms of the curve, what that's telling us, okay, if we draw a T distribution, okay, so now we're looking at T instead of Z. Remember that 0 is right in the center. So that T star value, 2.086, on either side of the center, we'd have a negative 2.086 out this way and a positive 2.086 out this way. Okay, and in that T distribution where n equals 20, we're saying that that middle 95%, so this middle right here, that area 0.9500 with 20 degrees is going to be between negative 2.086 standard deviations below the mean up to positive 2.086 standard deviations above the mean. Now if you remember back with the Z-scores, if you look up the middle 95% or 0.9500, that'd be negative 1.96 to positive 1.96 if you're looking at a Z axis. Okay, for a 99% confidence interval with 14 sample size, so 13 degrees of freedom. So when you look up 99% confidence level with 13 degrees of freedom, well, here's 99% down to 13 degrees of freedom. We get 3.012. So T star equals 3.012. And you can use a similar explanation for this, that negative 3.012 to positive 3.012 would be the values here on the t-axis, and you'd have the middle 99%, so 0.9900. Okay, so that's how you use the table to look up the T star values. Okay, it's not too crazy. So since S is an estimate for sigma, okay, so the sample standard deviation is an estimate for the population standard deviation, we now estimate the standard deviation of x bar to be S over the square root of n rather than sigma over the square root of n. So for the confidence interval for mu, we have x bar plus or minus T star times S over the square root of n. Degrees of freedom, n minus 1. So again, all we're doing there, instead of Z star, we have T star. Instead of sigma, we have S. Okay, that's the only difference in doing a confidence interval for mu. Again, sigma is unknown. Okay, that's the key to this whole thing. As far as a hypothesis test goes, when you find a test statistic for T instead of Z, now it's T equals instead of Z equals x bar minus the mean. Okay, so the sample mean minus the population mean divided by S over the square root of n. Again, with degrees of freedom n minus 1. Okay, so the concept is the same. It's just using T instead of Z and S instead of sigma. Okay, so next thing we look at is to do an actual confidence interval. Okay, so number 2 here, it says the mean commute distance for a SRS, meaning simple random sample, of 28 college students is 12.6 miles with a standard deviation of 4.1 miles. Construct a 90% confidence interval for the mean commute distance for all students at the college. So a 90% confidence interval for the mean commute distance for all students, that means you're trying to find a confidence interval for mu, the population mean, because we're looking at all students at the college. Okay, so as we read through this, okay, the trickiest part on these is to recognize whether or not you're given sigma or not. Because remember, that's what this all comes down to. If you know sigma, then you're going to use the z distribution. If you don't know sigma, then you're going to use the t distribution. So when we read this, it says the mean commute distance for a simple random sample. So they're telling you took a sample of 28 college students, got a mean of 12.6 miles. What that's telling you is n, your sample size is 28, with a mean of 12.6 miles. That's telling you that x bar is 12.6 miles, and a standard deviation of 4.1 miles. Well, again, this is where it's tricky, or it could be tricky. Okay, when you read that sample of 28 resulted in this mean, this sample mean, and this sample standard deviation. Now, it doesn't say sample standard deviation, but it's implied that it's coming from that simple random sample, which has sample in it. So this means they're telling you that s equals 4.1 and x bar is 12.6. If they wanted you to use the z distribution, at some point they would have said the population standard deviation is 4.1 miles, or assumed to be 4.1 miles. They don't tell you anything about the population standard deviation, though. So simple random sample tells you that that sample resulted in a 4.1 standard deviation. So that tells us, because we know s, use the t distribution, not the z. Okay, so 90% confidence interval, we're going to take x bar plus or minus t star times s over the square root of n. So plugging in our values, x bar, we know is 12.6, plus or minus our t star value. Well, t star, we have 27 degrees of freedom, because 28 minus 1 will give you 27. So we'll take 27 degrees of freedom and a 90% confidence interval. So 90% confidence interval with 27 degrees of freedom gives us 1.703 for t star. Okay, so 27 degrees of freedom with a 90% confidence interval is 1.703. So 1.703 times s, which is 4.1, over the square root of n, which is square root of 28. And just be careful on that you don't put 27 there, because that was our degrees of freedom. It's s over the square root of n, where n was 28, your sample size. Just be careful of that. Okay, then when you go through and do the calculations, I want to see your x bar plus or minus your margin of error, which is the 1.073 times the 4.1 over square root of 28, which gives you 1.32. And then that confidence interval, just like before, the smallest value, 11.28, and then goes to 13.92. Okay, so what that tells us, we're 90% confident that 11.28 is less than mu is less than 13.92. Okay, so there's our confidence interval. You can write it either way, okay, either of these two ways. Okay, we're 90% confident that our interval contains the true value of the mean commute distance for all students. Okay, okay, number 3. Okay, the Human Services reports that the mean length of stay in the hospital for 100 sickle cell anemia patients was 5.3 days with a standard deviation of 7.6 days. We're going to construct a 95 and a 99% confidence interval for the mean length stay for all sickle cell anemia patients. So that's a confidence interval for mu. Okay, so now what it comes down to is, do we know sigma or do we not know sigma? Well, again, when we read this, we have 100 sickle cell anemia patients, so that's our n value. Okay, that's our sample size, 100. The mean length stay of those patients was 5.3 days, so x bar is 5.3 days with a standard deviation of 7.6. So the question is that 7.6 standard deviation, is that sigma or is it s? So is it the population or the sample? Well, they told you that the sample of 100 sickle cell anemia patients had a mean of 5.3 days and a standard deviation of 7.6. So that is a sample standard deviation, because they didn't say that it was population standard deviation of 7.6. Okay, so for the two different confidence intervals, the 95% confidence interval, okay, and 99%. Okay, we'll do those two. X bar plus or minus T star times S over square root of N. Okay, so X bar was 5.3 plus or minus, well, the T star for the 95% confidence interval with 99 degrees of freedom. Okay, so when you look up that value, a 95% confidence interval. Okay, so we're looking at this column, and we have 99 degrees of freedom. Well, when we go down and look up 99 degrees of freedom, notice that that's not in the table. Okay, now different books will tell you different things. Okay, so it skips from 80 up to 100, okay, in this table. Other books may have different tables and different values in the table. Or that they might show different values for the degrees of freedom. Okay, so this one skips from 80 to 100. Okay, now some books will say use the closest value. What I look at, though, is you want to be as conservative as you can with your confidence interval. Okay, so what I would look at is doing the margin of error to be the largest that it can be. Okay, so if you look at the 80 compared to 100, 1.990 is larger than 1.984, which will give you a larger margin of error. Which you think about, well, gee, that's not good to have a larger margin of error, but it's erring on the side of caution, okay, because it's going to make our interval wider. Okay, so we're going to be, when we construct our interval, it's going to allow more values in. So again, it's allowing us to be more cautious. Okay, so I'm going to use 1.990 for that T star value, times S over square root of N, which will be 7.6 over the square root of 100. Okay? As long as we're looking at the table here for the 99% confidence interval, so if we're looking at the 99% column and 99 degrees of freedom, okay, I would use 2.639 for this one. Okay? Okay, so when you go through and finish that up, okay, for the sake of time, if you need to pause the video, go ahead. Okay, but that would, okay, there's your answers for the two intervals. Okay, so for the 95% interval, it gives us 3.79 less than mu, less than 6.81. And then the 99%, again, allowing more values in because we want to be more confident. Okay, so the same concepts apply. Okay, if you become more confident, you have to allow more values in. So 3.29 to 7.31 is a wider interval than for the other interval. Okay, so we're 99% confident that our interval contains the true value of mu. Okay, between 3.29 and 7.31. 95% confident that 3.79 to 6.81 will contain the true value of mu. Okay, so that's if you're given in a word problem where they give you the mean and standard deviation. Okay, the other type of problem you can be given is you're just given a list of data. Okay, so if we look at the lengths in minutes of 12 movies, so we took a sample of 12 movies, and one movie was 108 minutes, another 112, and so on. So just assume we took a simple random sample. Okay, I didn't say it, but just assume that. So we're given 12 movies. We want to construct a 90% confidence interval to estimate the mean length of all movies. Okay, and we're going to round to the nearest tenth in our final answer. Okay, so what you do here is you want to find the sample mean and sample standard deviation. So that's where you can enter the values into list 1 in your calculator and calculate the 1-bar stats. Okay, and what that'll give you, it'll give you an X bar value of 105.583 and S, not sigma, we're looking for S because it's a sample. The sample standard deviation is 7.763. Okay, and again, n is 12 because we had 12 movies. Okay, so again, that's just doing work in your calculator. I'm not going to show you on this. This goes all the way back to chapter 2, okay, where we did, where you found the stats in your calculator. Okay, so to estimate the mean length of all movies, we're trying to estimate what mu is. We're given a sample here, so we're going to use the t distribution.